I'm Getahun. Today I'm going to demonstrate the second experiment about determination of local acceleration due to gravity. In fact, I have did a video last year for the last 3 students, but it's in Amharic for students that do not listen or speak Amharic. Converting it to English is looks most. Therefore, you may follow it in either English or in Amharic. So determination of local acceleration, we have a setup look like this one. Here we have stand, we have a wire of length L, we have a bob. Then at the bob is in equilibrium position, it will have net force of zero, the upward force acting on the bob, and the gravitational force downward. The net will be zero at equilibrium position, but if we displace the bob to a certain angle in this direction, the bob will move here, then return back to here. It will have an acceleration given by this formula, minus g sine of theta. By applying Newton's second law, you can get this formula. But in order to have simple harmonic motion, or what we call SHM, the angle needs to be fixed. It has to be small enough. If we assume that the sine theta becomes equivalent with theta, then substituting sine theta gives us at equals to g minus g theta. Again, if you consider the relation between linear and angular parameters, theta is given as the product of tangential x, the ratio of x to L, and substituting theta instead of xl gives us tangential acceleration as minus g is equals minus g x power L will be the tangential acceleration. Now, as I've told you there about simple harmonic motion, in simple harmonic motion, the tangential acceleration is given by this formula. That means the tangential acceleration is directly proportional with the displacement, but inversely proportional with that. But in opposite direction, I mean the negative sign shows that one. Then if we compare this acceleration in tangential acceleration to be equivalent, we will have this relation. From this relation, we can derive, here we have negative, the negative sign cancels negative sign here, and x cancels with x here, and this equation becomes omega is equals to minus g over L. Minus g over L becomes minus g over L. But from your knowledge of period and frequency, the frequency is given as 2 pi over t. If you substitute omega in this equation, you will have this one. Again, solving for g gives us squaring both sides and rearranging the equation gives us the gravitational acceleration as this equation, 4 pi squared L over t squared, where L is the length from here to here to here, and t is the time required in order to cover single oscillation. That means as the bob moves from here to here, then return back to here, it will have one complete oscillation or one period. Therefore, that is the time. We square it and we will get the local acceleration due to gravity. Let me demonstrate or tell you a little bit with demonstration I got from laboratory, the Colorado Feds. So to demonstrate, first of all, the procedures are: first, you need to measure the length of the wire from here to here by using a ruler. Let's measure it. From here to center, it is about 0.7 meter. It has been mentioned here, 0.7. It's the length. Again, we have a stopwatch here. Don't remove the ruler. Then let me show you how okay. We will move the bulb to certain angle. We might move it in this direction or in this direction. Okay, or not here. Then we move it up above to 10 degree or less than 10 degree. Then I turn on my stopwatch up to 10 oscillations, measuring the oscillation of single. So the time required for single oscillation is, somewhat tedious. It's a difficulty. Therefore, we made it to measure about 10 oscillations time. So the stopwatch tells us the time, and this will tell you the trace. And we remove it, then we need only as the bulb comes to here, we start to record our time. Okay, 1, 2 oscillations, 3 oscillations, 4 oscillations, 5, 6, 7, 8, 9, 10. I stop it. It's about 16.92. To compute the gravity, the period is this one. The time for 10 oscillation is about that one. Okay, to that I developed a short the two-line code. Then the time we have here is the length is 0.7 in meter, and the time we have is in this case point, I think 16.92 exactly. Let me substitute those values. 90.6. Let me evaluate those values now. Okay, this equation 16.92. Okay, let me run the code. Okay. Local acceleration of gravity 9.65 in meter per second square. This demonstrates in your day's work, you are going to use locally available materials and fill this table as your data. You will change the length in 10 centimeters. 0.5, you will start from 0.5 meter, then 6, 7, 8, 9, 10. One thing I forget here, let me show you. One thing I would like to add is in this experiment, you will also see the change. What will happen if you increase the length to the period? To show that, let me go through once with the okay, this one. Okay, pause it. Border equilibrium. Okay. Both are at the same location, about 13 degrees. In fact, you may fix it to 10. Which of the two objects? This one has longer length and this one has shorter length, but they are displaced to the same angle. Then what will happen if we displace them? See to separate. Wow, this one is faster than this one. Therefore, as the length increases, what will happen to the period of the oscillation? You will conclude that from your today's experiment. So you will feel this variation changing the length will also tell you something to say about the period of oscillation. This is what I have for you today. See you for next time. Bye bye.